seminar after this nice presentation. So I would like to introduce Irene Fonseca from Carnegie Mellon University, and she will speak about variational methods in processing and the mathematical analysis of novel advanced materials.
Well, thank you, and I would like to start by saying that I'm deeply honored for having been awarded the Kirk Fellowship. I feel a heavy weight on my shoulders. I will try to respond accordingly. So actually the underrepresentation of minorities in STEM fields is a subject that's very dear to me, and in particular of women in mathematics. And actually one thing that I'd like to point out here is that in the 2 times I've been here at the Institute, a couple of weeks ago and now, in this program of design of new materials, it's been very rewarding to see the number of women that are coming here through the program. So that's really amazing, and I would like to congratulate organizers for definitely putting an effort into that. So what I would like to do today is to use this fellowship to convey to you the magic of mathematics, if you wish, the beauty that the mathematics concepts have in terms of unifying, in terms of a mathematical language, challenges and problems that may come from completely different fields. So what I chose to do today is to concentrate on energies that will involve different dimensionalities. So you have terms that say look at surface energies, you have terms that look at volume energies. There will be competitions between these terms, and nice things are going to result from that. By the way, I should say as a disclaimer, there will be no proofs, but everything I'm going to say is has a proof behind. So unless, of course, I say it's an open problem, I'll be happy to give you references afterwards if you're interested in knowing more about them. Although, as I go through, there will be some references on the slides. But basically, what I want to go to is the context. Why do we care? What are the mathematical tools? What are some of the results that we obtain? And whether we actually answered the initial questions, yes or no. So I will then take these energies that involve these different terms, and I'm going to treat them into completely different areas of application. And one is denoising, so PD methods for denoising in computer vision. And then, because this is the program of design of new materials, the second one will be on materials. So it will be the study of man-made nanocrystalline structures from superconductive materials. And these structures actually have a name. They're called quantum dots. And the way that they assemble, the way they are created, have an impact in their properties, in their rigidity and conductivity properties. And the reason why we care, it's because these quantum dots are behind the technologies that permeate our daily lives, from your cell phones to you name it, they are there. And so, and as you'll see, these quantum dots or islands, as they evolve, often they create defects in the materials, which in turn have also interesting properties. So let me then start. Here it is. So as I said, we are going to talk about energies that look like so. So they depend on a certain domain omega, and of course, depending on the context, omega will play different roles. There will be some field U, maybe with some gradients. It could even be higher order gradients. That's a volume integral. And then you're going to have a surface integral. S is a surface. So if omega is in Rn, S will be some, think about a manifold in one dimension less, say in Rn minus 1. This is the usual surface measure, if you wish, in Rn minus 1. There will be an energy here, depending on nu. Nu is the normal to your surface, right? You're going to have a surface with some normal nu, and so you may have what we call an isotropic surface energy there. As I said, for example, you can think of S as to be the boundary of omega, or you can think of U as being a field that most of the time is quite nice and has a gradient at places, but could have jumps. And so the jump set is that set S. So what omega S and U are will depend on the context. As I just said, I'm going to take these type of formulation of energies, and I'm going to look at them into completely different fields with different communities interested in each one of them, although there are some intersections like myself. And so we'll start with image segmentation, and we're going to talk about well-known models in this community. In particular, we'll talk about total variation, which I abbreviate as TV models, Mumford, Shah, and others. And then when I'll talk about models in the material science domain, these, as I mentioned, we are going to talk about quantum dots. Again, these are these islands that form when you deposit a thin film of a certain material over a substrate. That would be the second part. Okay, so let's start then. So in image science, you may think of your omega as a rectangle R. I chose R so that it's a rectangle. So it lives on the plane, right? It's a product of two intervals. The function U is going to be the digital image, if you wish. So when you talk about black and white and gray images, your U would normally have values between 0 and 1. So an interval in the reals, 0 say white, 1 black, gray levels in between. But you can also think about color images, in which case you will have values in R3. And a typical model for that is the so-called RGB model, RGB standing for red, green, and blue. And so combinations, as you all know, combinations of these three channels will give you the whole spectrum of colors on the plane. So, but you can also go beyond this. The domain R, if you're doing videos instead of pictures, the domain R will then be, for example, for MRIs, would be 3D. It would not be on the plane, it would be 3D. Most of what I'm going to say actually works also in 3D. Okay, so the next slide is courtesy of Carola, who's here, and she's a local from Cambridge. And that's the way that you produce these channels. So this is how you're going to produce a red channel here. So you're going to look at, you're going to zoom in the eye of the dog. And okay, this is not I'm sorry, the definition is not very good. But basically, there's a lead in there. The lower lead of the eye is right there. Then you're going to zoom in again. This is what you see, and there is the lead in there. And so when you map this out, what you see here is this is just the digital picture, if you wish, of the pixels here in your photo. That's how you produce your channels. Okay, so we are looking at the image as a mathematical object. And so we like to apply mathematical tools to this object. And there are many ways in which you can do that. And I listed here at least 3. The approach I'm going to take here is looking at these models through the lens of partial differential equations, calculus of variations. In that framework, you should think of your pictures as most of the time will be constant, right? So you're going to have, say, if it's the sky, you're going to have lots of big patch of blue there. There will be regions with some detail. You would like to allow for contours to be sharp. So, in other words, in mathematical terms, it means that you should allow you to jump, say, from one color to the next in a sharp way, so that you have a sharp transition between the two. So, if you wish, you should not be very, very smooth. So you don't like to have a very you don't like to have many smooth jumps from one color to the other. You would like to have sharp images. In mathematical terms, that means that you're going to work with functions of bounded variation. So if you don't know what it is, don't worry. Just think about it. These functions which are nice most of the time, they have gradients most of the time, and there are these very nice sets where the function may jump. But the sets where it jumps are very nice. They're basically manifolds. They have a normal, well-defined, and so on. Okay, so there are many, many areas that you study using these tools, in particular from the calculus of variations and PDE in computer vision, and this is just some of them. I will talk about maybe not all of them, but a few of these as I go along. So let's start with image restoration in painting. So you have a picture where it was damaged, it was scratched, so somewhere. So you have an information outside the damaged region, D is for damaged, right? So in the rectangle minus damage, you know how the picture looks like. And the question is, can you extrapolate information from where you know it to fill in where you don't have information, right? So, and indeed, this is in painting from this picture that was used a fourth order PDE model. Now this, what you're looking here is actually, it's a picture, it's actually a fresco in a chapel in Zaragoza in Spain, and it was damaged with humidity and so on. And so there was a very well-intended old lady that decided to actually restore it, and well, it didn't work so well. And so then the Spanish government took over, since this is basically patrimony of Spain, and they cleaned it up, and then what they did was they restored it to the damaged situation, and then they actually used again an in-painting model with higher order total variation. I will talk about that in a second. And basically what you have here is the restoration from that, which is almost 90% accurate. So of course you cannot get 100%, but I think that you agree with me that it's certainly better than this one. And this is what it's like today. Okay, so this is another situation here. So this was a chapel in Ovetari in Italy, and it was bombarded during the Second World War, and so pieces of the fresco were laying on the ground, and some of them were covered and some were not. So those that were exposed to the elements of the color was washed out, but you had gray levels that remained. So you knew that there were all these edges where probably the color would change, but you have patches where you knew the color. And so here it's different from the in-painting. The in-painting that I showed before was you had no information whatsoever. While here I do have information. I have gray levels, and now the question that I ask is, can I, knowing these gray levels and knowing that I have this color in these patches, how can I reproduce color everywhere? You can also think of this as an inverse problem. You see, color adds depth to pictures. So if I'm going to send you, and you can think of this in terms of defense problems. So if I'm going to send you a picture, it will be a lot cheaper for me, digitally speaking, if I send you in the black and white and gray levels, right? But I would like to send it to you, most of it with gray levels, but with just some color, in such a way that when you get it on the other end, you can reproduce it with maximum fidelity. That is, that will coincide with what I have over here. Okay, so that's going to be the goal here. So I'm going to use the RGB model. So U0, which we will not know everywhere, but we would like to know everywhere in the whole rectangle R, again has 3 channels. But there will be this damaged region here where I will only know a gray level. A gray level is basically a contraction of the 3 colors. So you can think of it as taking the 3 vectors and make the inner product with a vector on the sphere. And the vector on the sphere could be, say, a third, a third, a third. So if you add it just with equal weights, the 3, most of the time, it's pretty good, and it does well. Okay, so this is basically what I said, that it's the goal. It's to get color everywhere. And so this is a typical model which goes back to Fatemi and Osher. It's called the total variation model. Why total variation? Because the first term here, it's what we call the total variation of U. That is, you take the derivative of U and you take its measure on the whole rectangle. Think about, again, a U that, an optimal U for you and for me, will be a U that has most of the time is constant, right? You have patches of red, patches of yellow, and then you're going to have jumps. You're going to transition from one color to another. So what is the derivative of U? Most of the time is 0, where U is constant. But then when you jump from one value to the other, it's going to see that jump. So what this is doing is what? When I want to minimize this, obviously, I want to minimize each one of the 3 terms. The first one just says, you'd like to have the U equal to 0, which is you'd like to have U constant most of the time. So don't jump too often, because if you do, you pay with this term. The last term says, I want outside the damaged region, I want you to look like the pieces I have that already have color, right? And this U, by the way, it's a U that's going to have color everywhere. And then on the damaged region, if I contract that U, it should look like the gray levels that I was given in the beginning. So you know the gray levels on the damaged region, that is this contraction, and you know the U with the 3 channels outside. These are called the fidelity parameters. So there are several people working on this. And some of the questions that you may ask are, first of all, what happened? Okay, so what is this contraction? I told you that most of the time a third, a third, a third works well, but sometimes you have to be a little bit more careful, and I'm going to talk about that. But also, again, if you think about that inverse problem that I gave you, what is the best damage region? So if I have on my end a picture with color everywhere, and if I'm going to send it to you with most of it gray levels and just some color, where should I put the color and how much, so that you can actually produce the whole thing? Okay, so in terms of this last question here, so you may ask, what are these contraction maps that do the work for you? So there's a whole theory on that. I'm not going to go too much into that, but in particular, there is a condition on an asymptotic condition that this L has to satisfy, which is basically has to be sublinear at infinity. But this is just to say that if you're interested, there's a whole literature on that. So now let's see. Remember, this is the model, right? And actually, I'm going to ask that I actually have maximum fidelity. I'll take lambda 1 and lambda 2 to be plus infinity, which basically tells me that this term better be 0 and this term better be 0. In other words, this is going to go away, and I'm going to just minimize the total variation, that is how often I'm jumping, when U is exactly equal to U0 outside the damaged region, and the contraction is exactly the one I was given. So that's the new problem, right? Again, I can take these to be just the average, and that's fine enough. Okay, so the first result that you get is that, look, If the damage region is not too bad, the problem always has a minimizer. This is always has a solution. By the way, why do we care about minimizers? Because we like to think that the world likes to minimize energies. And fields at the bottom of energies are somewhat stable. And so that's why we go and try to minimize that. Okay. Well, but this is not good enough, right? We want to have uniqueness, because again, if I'm going to mess up the picture, send it to you, you don't know what I'm sending you, and then you're going to use these models to put a color everywhere, you better find the one I sent you. So you should have uniqueness in this problem, right? So, so what are the conditions on the damaged region? And I can do it whatever I want, right? I have I cannot do that with the frescoes which are already damaged, but I can do that when I do the inverse problem. And it turns out that if I choose L, so the contraction map, so unfortunately, that neighboring colors are mapped into the same gray level, then I give you a simple example where you don't get uniqueness. Otherwise, there is a theorem where actually you're going to see that there is actually a mathematical theorem that involves calibrations, if you know what a calibration is, which gives you actually sufficient conditions under which you get uniqueness. Most of the time, the minimum requirement is that when you have, so S will be the boundary between colors, and if anything goes bad, probably it will start at the boundary between colors, right, if it's going to get damaged. So you'd like to have your model robust enough that if you mess up around those boundaries, you can reconstruct. Okay, so let me give you a simple example where if you get two neighboring colors that are mapped into the same gray level, you don't get uniqueness. Suppose this is the image I have. You don't know it. This is the one I have. I have a color C1, which is yellow here. I have a color C2, which is over there. And I have the misfortune of assigning the same gray level to color C1 and color C2. Then I go here, and I'm going to mess up an annulus around here with the common gray level, because they have the same gray level, of C1 and C2, right? And then I'm going to send this to you, and I'm going to tell you, okay, now go back to this model and find me a U which minimizes the total variation among all U's which are equal to blue, where you see blue, equal to yellow, where you see yellow, and you can put whatever you want on the annulus, provided it has that gray level. What you're going to give me is the smaller circle, because you minimize the total variation, which now is the perimeter. It's yellow where it was yellow, it's blue where it was blue, and here you just put the same gray level all the way up to there. This is not what I sent you. I sent you the one which was the bigger one. Actually, it doesn't look like it, but okay, it was supposed to be the bigger one. Okay? So you see that that's not good. As I told you, there are necessary and sufficient conditions under which if you have the messed up region, the damaged region, if it's not too bad, if it's Lipschitz, if it basically does not follow the boundary of omegas, so it kind of goes orthogonal or so, then having U0 reconstructible, which means there is a minimizer for that problem, it's unique, it's equivalent to solving a PD, divergence equal to 0 with some conditions. I don't expect you to understand much about it here, but just keep in mind that there is actually a theorem with a PDE involved. So, let's go over this again. So suppose that I'm going to send you this picture here in just gray levels. I'm going to give you a little bit of color. So you have some red dots in here. I don't know if you can see in the back, but you have some yellows in there. And you take that model that I gave you, and I ask you, can you reproduce color? And this is what you're going to get. Actually, this was reconstruction by Fornacier in March. And so in terms of a cartoon, this is what you have. So this is what I'm going to give you. Some gray levels with some color. I am periodically distributing it in cells which have basically the color is inside in a smaller cell. These are the cells with gray levels. By the way, they don't need to be squares or rectangles. All you need to do is to have periodic cells which do not degenerate in, say, needle-like structures, right? But as long as you don't have that, the whole thing, if you can do a tiling with other structures that do not degenerate, it's just as fine. Okay, and so the theorem says that even if I don't have any information on gray levels, and if my damaged regions are contained, as I just said, inside these in the complement between these two squares, which is what I wrote here, and if you take a minimizer for this problem outside the epsilon, if you wait long enough, eventually they're going to converge to the real thing, to the actual, the full colored picture. There is a catch, which is that indeed the theorem behind this says that if I give you enough color, this is telling you that, okay, that where I'm giving you color, which is this W epsilon, size W epsilon, of course it should be smaller than epsilon, but on the other hand, not too small. That's what this is saying. Then indeed, this is always true. And it's an if and only if, because this is optimal. You cannot do better. We actually have counterexamples where if you give me less color, I will not be able to do it. Okay, now in terms of denoising, most images that you acquire come with noise, and you want to filter out that noise. And so here, this is basically the image that it comes corrupted. And again, you want from this corrupted image now produce an image which is clean and as close as possible to the ground truth. And again, so what you do is again a minimization of a volume integral. So you want to stay close to the corrupted image in some norm. I put the L2 norm, but it could be some other norm. And this again is going to be a regularizing term that is going to look at surface energies. So for example, in the case of the TV model, which is what we've been studying just before, this was just a total variation, but it could be something else. And you may ask, actually, maybe I can do better. Maybe the TV model, it's not quite good for all possible pictures. And so here it is. So this is actually an MRI picture. This you have the clean image, and this is the image that you get, which has been basically modified with a Gaussian. These kind of pictures, we use them to test the model, because when you're going to use training, learning schemes, you need to have a collection of clean images that you know that they are the ground truth and the corresponding messed up or noised images. So again, let's look at regularizers. So this was the model. Remember, you want to stay close to the image that I was given, which is corrupted, but that's the best I get. And then the question is, can I do better than TV model here? This is the rough model. Sure, you can play with parameters in front. Of course, the value of alpha is going to determine whether you penalize too much making sharp changes or not. The other models, for example, the Manfred-Shah model, where the U's are going to be also bounded variation, but they're special. They don't have a counterpart. And instead of taking the TV model, you take something which it's super linear, but it looks at a jump set of U. So if you go back here, as I said, the value of alpha is important. So if alpha is too small, is very small, then I can afford to have a big variation, so I can afford to have a lot of detail. But if alpha is very big, this better be small, which means U is most of the time constant, And so you're going to lose, there is going to be over smoothing, and you're going to lose a lot of details. So of course, that is the first, it's step one in this process, right? It's what is the alphas. Okay, so this leads to parameter bilevel training schemes, and going back to the work of Carola Viviane Schoenlieb here with her collaborators. And basically, if you're just looking at tuning the parameter, what you can do is, okay, you have this family of regularizers depending on alpha. For each one of them, you find a minimizer, and then you're going to optimize on the alpha. Among all these ones, which are the ones, what are the alpha that actually gets you close to actually the ground truth? That's a semi-supervised training scheme, because you do know, you know the ground truth, and you know the noise image for a training set. And then the point is, once you fine-tune this model, then you throw in here you added that you don't know. You see that you don't know. Okay, so but let's keep looking into this, because maybe you can do even better. So if you look at these pictures again, there are areas. Why should I use the same, just multiply by a constant parameter? Why should I use the same regularizer all over the place? So for example, if I am in places like these, I don't need a lot of detail. But right here, for example, I want to have a lot of details. So maybe what I need is actually alpha, not just a constant, but maybe depending on position, right? Because right here, I can afford to have a huge alpha, so that the derivative is constant. Basically, it's so u is 0, so u is constant. But here, I would probably like to have a very, very small alpha to allow to have a lot of details. So you could have alpha here depending on x, okay? And you can even go beyond that. And why should you just stay with first order? What about second order? Look at, for example, this type of model, which again goes back to the work of Carola and her group, where here, what are you doing? You're trying to now minimizing by looking at maps V that want to look as the derivative of u, because you want to minimize this, and in turn you take the symmetrized gradient of that. So this smells like a second order derivative for you, right? And again, you have this training scheme, and now you may say, okay, so maybe now I can have the flexibility of not just looking at alpha times TV, but also now compare that with other terms like so, right? So now you have more freedom in the choice that you're going to penalize these transitions. And I don't want to go into details, but this could be even more generalized. And again, you're going to recover, there's a full theory where that includes all these models, TGV alphas and TVs, etc. Just to give you an example of a numerical simulation, this is the clean image. I messed it up here, and then you're going to reconstruct with regularizers. And for that, again, I'm going to compare. The bottom line is that in the end, you want that the distance between what you get and the clean image is as small as possible, right? You want to be very, very close to the real thing. And so there's a cost value that depends on that parameter, what kind of PDEs you use, etc. And it turns out that for this type, this is just a simulation, that for this type of PDE, I can show that actually I can do better than what you do by just using the symmetrized gradient, which would be this one here. And I don't expect you to follow all these parameters, but basically I'm saying that, interesting enough, I can do better with parameters about 5% better, with parameters that are not quite the ones you'd normally expect, which is that you just put the same weight everywhere. Okay. This concludes what I want to talk about, what I wanted to tell you about how you use these energies that involve bulk and surface energy for imaging, and now I want to take that into the realm of quantum dots. So what is the situation here? Completely different. So now you have to switch gears completely. And the situation is the following. You're going to have a material, an elastic material, which has a certain crystalline structure. That's a substrate. Think about silicon. And on that material, on that substrate, I'm going to deposit a very thin layer of another material that is, in terms of its crystallography, not too far out, not too different, but just a bit different so that they don't like to live together. So, for example, silicon, germanium over silicon. Now, what happens is that you have these two materials that you are forcing to cohabitate. They have different crystalline structures. And until you reach a certain thickness of the film, so if the volume of the film is very small, we all know that surface energy dominates volume in that case, right? And so the film will try to stay flat, minimize the surface energy, although there is now some bulk energy, some strain energy being formed at the interface between the two. As you increase this volume of the film, now you're increasing volume, and you're increasing elastic energy, and at some point, something has to give. And what gives is that the surface of the films is no longer planar, and islands are going to form. So now you pay more in surface energy, but by doing that, you're going to release bulk energy. So there's going to be, again, a competition between surface and bulk energy. This is basically what I just said. You have the surface is flat until a certain critical thickness, which, by the way, we know what this critical thickness is. And then at some point, this is basically what I just said, you have a competition between strain and surface energies. And this is a very naive cartoon. You're going to have now that you have the surface that now becomes corrugated. You can imagine that you have the substrate is living here. The film lives between basically y equal to 0 and y equal to some function h of s, which is just the graph of the film. Okay, there are several ways in which these, and by the way, these corrugations eventually take the name of islands or quantum dots. What you see here is the formation of quantum dots in silicon 0.8, germanium 0.2 over silicon. And there are several ways in which these structures form. I don't want to go into that, but the one that we're going to talk about here is the SK model. Okay, so, and why do we care? As I said, it's not that you want to avoid quantum dots. You want quantum dots. Quantum dots have interesting properties, provided you have some way of controlling, anticipating, understanding how they form, how they evolve. For example, as we'll see shortly, their shapes are important, and they evolve with volume fraction. And so, and where they are, their shapes, their sizes, influence their optoelectrical properties. And actually, last year, I think, or last year, on CNN, you could see this Samsung monitor for your home TV that was using By the way, it was not me who said this. This was on CNN. It was breathtaking and exhilarating, etc., using quantum dots. So that's the technology behind this. At the time, it was $1,300. Now maybe cheaper, but basically that's that. So we care about this because these things really do permeate our lives. And of course, also in 3D printing, you use properties of quantum dots in the laser beams. Okay, so a couple of things we are going to study here. Some of these are properties that our colleagues in material science know for decades, and they actually approached us to see if, with the models, phase field models that they were using, if we could validate their what they see in experiments and simulation. The first property is wetting and zero contact angle. What is wetting? Wetting is that, so when you let the system relax, and when you look at it, often it looks like the substrate is exposed, but actually, when you look at the energy, it's not quite so. The film actually covers everything with a thin film of just a few atoms thickness over the substrate. That's why we call wetting, because it's like if it's wet everywhere, although it may look like the substrate is exposed. Zero contact angle has to do with the way that these islands meet the substrate. So in our language, what it means is that the profile H, right, which was the profile of your film, will be better than Lipschitz. Lipschitz, you have an angle, right? You can have an angle when you meet the substrate. It has to be better. Zero contact angle means C1 alpha. You meet nicely and smooth the substrate. So that's a regularity result, right? For a free boundary problem. That's what it is. Then what you do is you study at the quasi-static level, so just in terms, no evolution, no time in there. You just look at the relaxation of the energies, you look at the minimizers, properties of minimizers. Do they fulfill what our engineering colleagues have believed and have witnessed for decades? But then you let these things evolve. And you let them evolve by surface diffusion, right? You use Einstein's Earth equation, you let them evolve, and what happens after some time is the following, is that they will start very nice and smooth with zero contact angle, but then at some point as they continue evolving and as you continue putting more film into the system, some of these islands start coming together. They form cusps. When they form cusps, you have a problem because it's no longer a graph, right? So your model cannot go through. And at the bottom of that cusp, you're going to create a lot of energy. So a miracle is going to happen in that although dislocations, material defects cost a lot of energy, they are energetically more favorable than having all these cusps forming in your film. So what's going to happen is that, now I have a slide for that. These locations will form at the bottom of these cusps. They will migrate down to the substrate, and the film becomes flat again. And you start all over. Of course, there's a caveat, which is that if you have a cross slice of that, you'll see that you have nucleation sitting on the substrate. Okay, so, and by the way, there's a lot more to this than what I'm going to talk about. In particular, you can also consider the case where you have these free atoms that jump from on the steps of the surface. You can use the Giorgi minimizing movements and so on, but that's not for today. Okay, so, simple cartoon. Suppose that these things were self-similar, say with an axis away from the board, and that I just had a cross-section. By the way, they aren't. They're actually 3D formations, and you cannot simplify like that. But as you see, interesting enough, we can do the evolution for 3D. Most of what I'll say for the regularity and for minimize of energies, it only works for 2D. So there's a lot to do here. We are just beginning to understand what's going on here. So it's an extremely rich field with tons and tons and tons of open problems. So, but let's assume for simplicity that I could assume that this is, say, that you have self-similarity away from the screen. And so here's your substrate, lives here. I'm going to assume that I will work on periodic cells, say and that the thing repeats itself, say with B. Your film lives up here in what I call omega H. So this again, it's silicon, this is silicon germanium, and that is the profile of your field, of your film, which is going to be a free surface because a priori I don't know how it looks like, right? So you're actually going to have two unknowns here. And again, bulk versus surface. On the film, I'm going to have an elastic energy. And then up here, I'm going to have an energy that depends on the normal. A lot of what I'm going to say, you could take psi to be 1, so you just look at the length. And putting psi or not psi is the same. For evolution does make a difference. And it should be, right? Because as I say, what really drives all this is the fact that you have two crystalline structures that don't like to live together. So the crystallography plays a role. And when you look at the evolution problem, for those of you who know what I'm going to just say next, it's interesting to observe that the shape of the Wolf set is fundamental. If you don't know what the Wolf set is, just that's fine. Let's move on. Anyway, so these are all very small deformations. So my U is not a deformation, it's a displacement. And I'm going to use the symmetrized gradient of U as the strain, as usual. So we are within linear elasticity. W is your typical bulk energy density for elasticity. So this is, it's basically an elliptic system. It is a positive definite fourth order tensor. Actually, normally, and C captures the material properties of the material. So you should actually have a C1 here and a C2 there, and that can be done. It was done by two PhD students, former PhD students of mine, now in Vienna. So how am I going to mimic the fact, so if I'm only going to work up there, how am I going to mimic the fact that the two crystalline structures are different? This is what I'm going to mimic, is that I'm going to assume that the natural state here, so bottom zero energy when the substrate is happier, is when U is 0, so do nothing, while I'm going to assume that the film here likes to be sheared inside the 1, 0 direction. So there's going to be a parameter E0. E0 is a positive constant. If E0 was 0, you would have the same, so there'll be no difference. But I'm going to anchor the film here by saying I want it to be comfortable with the film, but uncomfortable with the substrate. Okay, so I'm going to minimize this energy, subject to the constraint that the amount of film that I have is fixed. It's D. So I give you a bucket of film, it's D, and you're going to work with it. And you're going to see, you're going to pour it, and then you're going to see how this thing is going to eventually relax. There it is. Okay, so this is basically what I just told you. I'm going to assume that they share the same elastic tensor, but you can also do it with different elastic tensors. I have lots of references here. Again, as I said, I'll be happy afterwards to give you more if you so wish. Okay, so let's say for simplicity, although this does not take anything from the problem, that psi does not quite depend on the normal, but it has only two values. And if I'm on the film, I have a certain surface energy density, and if I'm on the substrate, I have a certain, different constant, right? So I have two constants. This is if I'm on the substrate, y equal to 0. This is if I am on the film. it turns out that if you minimize this and if you relax this system, if you look at the states of minimal energy, it turns out that indeed you're going to get wetting, in that the relaxed effective energy there is, if you wait long enough and see how when it is more comfortable, the bulk energy stays the same, but actually the substrate energy density disappears from your problem, and it's like if you have film everywhere. So you see wetting. So that's the conclusion. You see wetting. Now what about regularity? Remember that I said that these islands should meet the film very nice and smooth like so, right? C1 alpha. Indeed, you can prove in all regularity, you can prove that that the film, the profile is Lipschitz, which is not good enough. But actually, there's even another caveat. Except for possibly a finite number of cusps or vertical slopes. And so when you have a situation like this, it's no longer a graph and your model stops here, right? Then you have to use varifolds or something else. And actually, you cannot do better. So we tried for a long time. We knew that could only be finitely many because forming one of these things costs a finite amount of energy. So the energy is bounded from below. So of course that means that you can only have finitely many if you start with a system that has finite energy. And we worked for a long time to try to actually get rid of them. But indeed, these things are observed. And in silicon 0.6, germanium 0.4, you do see these features. So you cannot do better in all this regularity. But you can do better if you assume that you have not just your usual linear elastic model, but if you have isotropic material. For isotropic materials, this is your usual strain energy density. Lambda mu are the Lamé moduli, which satisfy these properties so that this is positive definite, so that you do have your ellipticity. And in that case, again, as I said, in general, you can always say it's Lipschitz, so you could meet at angles away from this finite number of singularities. But now, if you assume it's isotropic, you can do better. And away from the singular part, which we know it's finite, these are cuts, these are cusps, it's actually C1 alpha. And so you get zero contact angle. So it's really very nice and smooth away from those. And so that's the picture you should expect to see. Okay. So what about the shapes of the islands? And it turns out that the shapes of the islands do evolve with volume. As I said, if you have very small volume of film, you don't have islands at all. The film is flat. Then they start forming. And it turns out that there is a whole hierarchy of shapes. And we have done work with several people who are listed here. Again, this was already known. And so we were led to this by our colleague Tersov, who he works at IBM. For obvious reasons, they are interested in this. And so these were simulations from Brian Spencer and Tersov. And indeed, with analytically, we could validate that you go through this hierarchy of shapes depending on volume fraction. Okay, and so in 5 minutes or so, I will now go to basically the punchline, which I think is absolutely remarkable, which is this formation of dislocations. So here is a cartoon. Well, actually, it's not. This is actually an experiment where you see the islands forming. That's your substrate. The islands are there. Eventually, they are going to increase in size. They're going to come together. You're going to have a lot of energy in the film. And what happens is that, as I said, let's look here. Here. You see that you're going to have dislocations forming at the bottom of these cusps. They migrate down to the substrate, and that's what you see. and they are here, and then the film now becomes flat again. This is a true story. This is not fantasy. And so, so actually nucleating these defects, it's a way of releasing energy. And there are many questions here that we have not yet understood. For example, all pictures that I know of similar experiments show the dislocations arranged in a periodic way on the substrate. We don't know how to prove this yet. So it would be interesting, even in a 2D kind of setting, which again, these things are not 2D, but even with that huge simplification, as far as I know, there's no results on periodicity of such. Okay, so these locations, okay, this is the usual cartoon, right? So you have a defect, you have an extra layer of atoms that appears here, and the way that mathematically you're going to control this is by looking at the Burger's vector. And the Burger's vector is what you pay when you go with a circuit around this extra layer. You're going to have a gap there, so the circle will not close. And this Burger's vector is a measure of the dislocation that you have inside your loop. So, so what happens is that while before my H was gradient of U, so curl was 0, was curl free, now my H can have, the curl of H can actually be concentrated on a curve gamma. So here curve is just a vertical, it's just this vertical dotted line. Which is going to be the Burger's vector tensor times the tangent to this, to the dislocation line. So, and here you have the edge dislocation and typical screw dislocation. But this is going to be the difference between having no dislocations, curl equal to 0, versus curl equal to something which is different from 0. So again, let me assume for simplicity that I work with straight dislocations. So I can look at the cross section, and they will all go through, say, some points which I'm going to call Zi. Z1, Z2, Z3 will be these points on the midplane. And again, the curl in this case is just the Burger's vectors times Dirac masses at these points. And it turns out that, okay, you cannot just plug these into the energy you had before because you get plus infinity. And actually it's known that if you stay away radius epsilon for dislocation, it goes like log epsilon, so it's bad. Usually there are two ways of doing this, and one is you go back here and you remove a cylinder around the dislocations and you stay away from the dislocation line. Another way is to mollify, is to say, okay, of course I cannot plug these into the energy, but let's mollify these with your usual modifier, and then of course a smooth function, just plug it in there. Okay, so that's basically the way that you do this. In what I'm going to say here in the next couple of minutes, I'm going to actually mollify. Remember, sigma is just a density. Sigma is this. It's the density. I had it somewhere. Maybe I don't have it anymore. Yeah, it's in here, which is a dislocation measure. If sigma is 0, you have no dislocations. And so you take that, you mollify with your typical mollifier, and then you plug it back exactly in the same energy we had before, right? Linearly isotropic material, except now, and you symmetrize, because you should have grad U plus grad U transpose over 2. Now you symmetrize H, which could be curl, non-curl free. And again, you're going to pay some surface energy. This is a singular part. In the singular part, after you relax, when you have cusps, you pay twice, because you have to go down and up. So forming a cusp, it's basically the result of having these two energies that come together. Okay, so what you can ask is, so suppose that I have K dislocations of my disposal, and I have K Burger's vectors. what is the optimal configuration for them? Where should they be placed in my system? And so again, you go back. So now your energy depends on the dislocation measure, on H, and on the profile, right? You still have the profile of your film. Okay, so again, you have a fixed amount of film that you can work with, which is this. Same result, it has a solution, and even more, the regularity is still pretty much the same, except for finitely many cusps and etc. The film meets at 0 contact angle, so it's very nice, C1 alpha. But then, I'm going to read through you what this means. And this means the following. Suppose that D was the volume, how much film I was giving you. Suppose I give you enough film. E, remember that E was the mismatch between the two lattices. Suppose that you have enough mismatch. Gamma is the surface energy. Suppose you penalize enough the surface energy. Then, any minimizer will always have dislocations, and the dislocations lie at the bottom. Okay, but then you say, well, but you're cheating, because you're allowing for dislocations, but you're still using the same energy which was for a non-dislocation model, and dislocations cost. Fair enough, so let's go over that again. And I'm going to take my energy, and I will use classical energy costs to form dislocations. This goes back to Nabarro. And you add that. So now if I have dislocations, okay, maybe I don't have free lunch here, because now I'm actually, it's not just the classical energy, but now I'm actually paying directly in forming. But still, you're going to see that, again, if you have enough volume, if you have enough mismatch, if you pay enough in terms of surface energy, then indeed, even if by adding this extra energy, you always prefer to have dislocations, which validates the pictures we saw. Because you had dislocations there sitting at the bottom, the film was flat, and yes, and the film becomes flat. Finally, okay, there are many problems here which are open. In particular, I should say that for the evolution problem, which I did not mention, you start with a certain profile that then you let evolve. We only know how to do this when the initial profile stays away from the substrate. So if I give a profile that, say, touches the substrate at places, it kind of gets pinned down there. We don't know how to let it go. We don't know how to prove uniqueness in 3D, which is where this should be set up. At some point, you're going to get these profiles which no longer look like graphs. Our analysis stops there, but maybe you can use other tools. Like I just said, if that resonates to you, things like varifolds or something like that. We talked about, okay, there are several ways of doing surface diffusion, but I did not mention that. We are now doing work with Amazo and Leone on the wetting, which is the reverse process from wetting, and then dislocations. So what I mentioned to you was when the dislocations were just straight lines, but dislocations can actually be mixed dislocations and could be curved, and this is a much more complicated issue. We are basically wrapping that up right now in the first go. There's also Tom Hudson in Warwick. Tom Hudson has looked at curved dislocations. Tom Hudson uses the modification, what I did before, while here we actually use the other method, which is to remove a core around the dislocations. But that would be another talk, and so I think this is a good place to stop. Thank you.
So, if I understand correctly, you assume that the surface of the substrate is sort of looking nice. But then if you wait long enough, then you have these dislocation would appear on a periodic kind of structure. So it sounds like you're introducing some kind of roughness to the surface of the substrate. So I'm wondering whether there would be a homogenization effect.
No. There's no homogenization effect here. What is just actually pure competition between surface and bulk. The films that I'm not assuming here that I have mixtures of different films or anything like that. So there's really no homogenization. But what happens is that up to the point where the dislocations form, you still have graphs, and they're pretty nice. It's exactly what I said. They are actually C1 alpha, except for this finitely many, but it's finitely many, so we know how to control that. You don't have like accumulation points, say, going to the boundary and having a failure of the system. No, it's finitely many. They're like 5. And so you can't track exactly what's happening there. You know, you just blow up what's happening there, and it's a very nice graph that eventually, of course, it's going to become, it's going to coalesce, and then yeah, I mean, we have to stop. But when that happens anyway, you know that there are these dislocations that come down, and then the thing flips back. So, but you can't control very well what's going on exactly because of this finiteness that you have there. And so because they're finite, you can do things, right? I mean, you can localize the problems. You can just say that, okay, I'm assuming that it's nice this way, it's nice that way, and something is happening here, right? And so you can make perturbations, you can make all that. If you had, say, accumulation points, you could not do that because you would start messing up with things that are around in the neighborhood. So the fact that it's finite, it's very important.
You mentioned vapor deposition technique and some models of growth. But in those models, and also if you do sort of atomistic simulation, you start with an empty substrate, and then you add, say, one molecule at a time or whatever. So you don't start with a film and break it down. But actually you grow in island, and then you have different models of growth, the Strasky and Strano that you've mentioned, or others. I didn't understand. Do you actually model that, or do you always start with a uniform film that breaks down?
I start with a uniform film that breaks down. So I don't model the deposition, which is what you're talking about. Yeah. I don't do that. So I start from when it's already been deposed, and that's at that process. That's where, for example, atoms make a difference because they can jump or not, and so how these steps are organized. That's that process. I start from already knowing that the film is already there.
If I may, the difficulty in that the boundary condition, at least in simulation, atomistic simulation, does change as the coverage of the substrate increases. So you start with a few molecules that lay flat, and when you get some critical coverage, sort of 50%, then they lay up. So somewhere there should be a change from a flat boundary to a perpendicular boundary. In some cases, at least, it's not always that.
Yes, but again, I mean, of course, what we've done has limitations, and that's one of them. First of all, we ignore boundary conditions because we have everything periodic, and so basically we are putting that under the rocks. So we are not looking at that. We just say, well, I assume everything is periodic, which is not. So that is the first limitation. And so right there, I don't see those effects because I take periodicity.
May I ask you, what are the principal difficulties in 3 dimensions? So there is a way of select some...
well, okay. So for example, so in 3D, for the regularity, we use the interior sphere condition argument, which actually hits the interior Wolf condition argument. And we simply don't know how to do that in 3D. That's one difficulty. Another one is that when you look at all Lagrange equations, it's always the same thing, is that you have liftings, because you can think divergence and gradients, you rotate and you have one or the other. So you can have liftings, and you have a whole thing of harmonic analysis that comes in. In 3D, we don't know how to do that. For the evolution, it's completely different, because in evolution, what you do, well, what we have done is to use basically an Euler scheme, a time discretization scheme, so a la de Giorgi, minimizing movements, and there you don't really see the dimension, it doesn't matter. You know, you just do these time discretizations, you do interpolations, and then you see where it goes. And that could be in Rn. But the regularity, it's the one that really uses 2D arguments.
But what about the kind of discontinuity that may form in 3 dimension, because it's much more complicated than
right, but even that we don't know.
Ah, okay.
No, we don't know. We don't know.
Do you have a
No, because again, the way that we, the way, for example, that we prove that it's finitely made is because you get lower bounds for those bad spots to form, and for that we use entirely 2D arguments. So, I mean, that being said, it should be done in 3D because these things live in 3D, and so, but you'll need to come up with new ideas, and so there's a lot to be done.
I have another physicist question, which is, you said several times that the amount of film is finite. If I think of it in terms of minimizing really the whole free energy and so on, the mismatch with the underlying lattice should actually determine the thickness of the film, at least under some conditions. And from what I understood you, the mismatch, and I mean, you just put the finite amount.
The mismatch is there since the beginning because I'm giving you 2 different materials, and so they are crystalline materials, right? So this one is cubic, this one is orthorhombic or whatever. It is what it is, right? So the mismatch exists from the point of view of the crystalline structure of each one of the materials. Then you put them together, right? And then what I said was that, and so then what you're going to, so different things happen for different amount of volume. For example, as I said, if the volume, what I call D, is small enough, nothing happens. And you can prove that the minimum configuration is the one that has film flat, H equal to constant, and nothing happens. It just stays like that. So, but if I give you a huge amount of film, I know that I'm going to start seeing things like that. So that's why it depends on D, because different things happen with the different Ds. And as I said, there is even, depending on the material constants, you can even quantify what is the critical D after which you go from flat to non-flat. So that can actually be quantified. But the mismatch, it's something that you work with since the beginning. I give you 2 different materials, they have different crystalline structures.
That's fine. I think that in some models, at least in some limits, the mismatch by itself should control the maximum amount of film that you can grow on top of another.
Oh yeah, sure, no, I understand.
It should be related.
Sure.
At least under equilibrium conditions, which is not what exactly what you do.
Yeah.
You know, these growth modes are not equilibrium. That's why they grow.
Thank you. Let's thank the speaker again.
Thank you.